Good morning.
Good morning,
I'm Usha
students.
Rani,
Today I am
Associate
going to
Professor
explain
from
about
Siddhartha Institute of Science and Technology. Today I'm going to explain the electron theory of metals. So in this electron theory of metals, there are different types of contents, that is classical free electron theory, quantum free electron theory, Fermi-Dirac distribution, effective mass of electron, sources of electrical resistance, and types of electronic materials. So these are the contents. And next, here, so classical free electron theory, let us go for classical free electron theory. So the main postulates are here. A solid metal consists of more number of electrons and revolve around the nucleus. The free electrons moving in a random motion in a metal. So before the application of the electric field, that is in the absence of electric field. So if you apply electric field on your metals, an electron moves certain direction that is opposite of the applied electric field. So it is a we know that it is a nucleus. Electrons revolves around the nucleus. So mainly here the free electron theory exists in three types of stages. One is classical free electron theory, another one is quantum free electron theory, and last one is band theory of solids. This classical free electron theory was developed by Trudy and Lorentz. So in this classical free electron theory, electrons in a metals obeys the Maxwell-Boltzmann distributive law. So, and also electrons in a metal behaves as a gas molecules in a gas container. So it is a kinetic energy is equal to 3 by 2 kT. So we know that in the absence of electric field, electrons are moving in a random motion. If we apply electric field on a metal, it moves certain direction that is opposite of the application of the electric field. So here the electrons required additional velocity. That velocity is known as drift velocity. So the drift velocity can be defined as the velocity of electrons in the steady state in an applied electric field is called as drift velocity. So the formula of drift velocity is equal to small e into capital E into tau by m. Here capital E is equal to application of the electric field, tau is a relaxation time, m is a mass of an electron. And what is the definition of the relaxation time? So here the relaxation time is a instant of sudden disappearance of an electric field across the metal. The average velocity of the conduction electrons decays exponentially to zero, and the time required in this process for the average velocity to reduce the 1 by e times its value is known as relaxation time. So mainly it can be defined as the time taken by electrons to reach the original position from the disturbed position. So, and next, mean free path. Mean free path can be denoted as lambda suffix c. So, the average distance traveled by the electron between two successive collisions is known as mean free path. So, on mean collision time, these are the basic definitions. The average time that elapses between two consecutive collisions of electrons with the lattice points is called as a mean collision time. So, tau is equal to lambda by v. Here, lambda is a mean free path. V is a velocity of electron. So here mainly in this free electron, we can derive an expression for electrical conductivity sigma. So by using the Lorentz force and Newton's second law of motion, we can derive the electrical conductivity. That is sigma is equal to n squared tau by m. And what is the success of free electron model? It explains the electrical resistivity in metals. It explains the electrical conductivity in metal. It explains the thermal conductivity in metals, and also it verifies the Ohm's law. But there are some failures in free electron model. So the main drawbacks in a classical free electron theory is it does not explain the optical property of the metal. It does not explain the magnetic materials of the magnetic properties of the metal, and also specific heat of the metals. So, and to overcome the drawbacks of the classical free electron theory, after that in 1928, Sommerfeld developed the quantum free electron theory. So, according to quantum free electron theory, here also for quantum electron theory, an electron is treated as quantum particle, that is tiny particle. So, to overcome the drawbacks of the classical free electron theory, Sommerfeld developed the quantum free electron theory. So in this quantum free electron theory, we can derive the same. electrical conductivity of a metal, sigma is equal to Ne squared tau by m star. So mainly here m star is a effective mass of electron, tau f is equal to relaxation time, N is a number of electrons per meter cube, sigma is equal to electrical conductivity. So here in the absence of electric field, these velocities cancel each other and net velocity in all directions is zero. So if we apply electric field along the direction, the electrons in the sphere experiences some force along the negative direction. So here, what are the successes? So the drawbacks of classical free electron theory is a success of the quantum free electron theory. So it explains the optical properties, magnetic properties, and specific heat of the metals completely. But there is some drawbacks of the quantum free electron theory. So that is, it is failure to explain the mechanical properties of metal, and also it failure to explain in atomic arrays in metal. And next, Fermi-Dirac distribution function. So the Fermi-Dirac distribution specify how many of the existing states of the energy E will be filled with electrons. So Fermi energy can be defined as the highest occupied energy filled with electron is known as Fermi energy level. Below the Fermi energy level, all the states are filled with electrons, and above the Fermi energy level, all the states are empty states. So here the probability that an available state and energy E will be occupied by an electron. So it is a probability distribution function, that is f of E is equal to 1 by 1 plus exponential function of E minus EF by kT, where EF is equal to Fermi energy level, K is equal to Boltzmann's constant. This is the value of Boltzmann's constant, that is 1.38 into 10 power minus 23 joule per Kelvin, and T is the absolute temperature in Kelvin. So it is, what is the effect of temperature on a Fermi-Dirac distribution function? So the effect of temperature means if temperature is turns to 0 Kelvin. So on here we can consider two cases. One case is E is greater than EF, another case is E is less than EF. If we consider E is greater than EF, then we can substitute the values in that formula. Then we get 1 by 1 plus exponential function of infinity. E power infinity becomes infinity, 1 by infinity becomes 0. That means 0 means, so above the Fermi energy level, all the states are completely empty states. And for E less than EF, for E less than EF, if you substitute that 1 by 1 plus exponential function of e power minus infinity. So e power minus infinity is equal to 0. 1 by 1 plus 0. Then 1 by 1 becomes 1. 1 means 100% probability. 100% probability means below EF, all the states are filled with electrons. So it is the graphical representation of the Fermi-Dirac distribution function when the temperature is greater than 0 Kelvin. So the graph shows between Fermi-Dirac function versus energy level. So here it is the graph like that. T is equal to 100 Kelvin and T is equal to 400 Kelvin. So here f of E on y-axis Fermi-Dirac distribution function. On x-axis E minus EF electron volts. So effective mass of electron. So effective mass of electron means can be denoted as m star. The mass of the electron in the periodic potential field is known as effective mass of electron. So the formula can be written as m star is equal to h square by d square E by dk square. This is about the effective mass of electron. And so solids are classified into three types based on the energy gap. So that is, we know that conductors, semiconductors, insulators. In conductors, conduction band and valency band both are overlapping each other. Overlapping each other means there is no energy gap between valency and conduction band. So that's why here energy gap is 0. So if this energy gap is 0, it completely supports the electricity. So if it is completely supports the electricity means the electrical conductivity is more. So examples of conductors are ferrous, cobalt, nickel, etc. All the metals are conductors. And next, semiconductors. In case of semiconductors, it partially allows the electric current. So in case of semiconductor, the energy gap between valency and conduction band is very small. It is about the 0.5 electron volts to nearly 3.6 electron volts. So in case of semiconductors, electrons and holes are responsible for electrical conduction. So the electrical properties of semiconductor lies between both conductors and insulators. So why? Because means here at 0 Kelvin semiconductor behaves as insulator. At high temperature it behaves as conductors. So examples of the semiconductors is mainly germanium and silicon, both are belongs to the fourth group elements. And in case of insulator, the energy gap between valency and conduction band is very high. It is nearly 7 electron volts. So in case of insulator, the conductivity is 0 because it does not suppose the electricity. It completely opposes the electricity. So that's why the conductivity is 0. So examples of the insulating materials are glass and plastic. So these are the examples. So it is about the electronic materials, that is conductors, insulators and semiconductors. So these are the references on NPTEL video lectures of the free electron theory. Thank you.